In section 5.3, we take up a little more advanced idea of integrating and finding antiderivatives. And let's start with this problem. And this will illustrate this in the next problem. We'll illustrate why we need this more advanced idea. And so let's suppose that we want to find an antiderivative of 2x plus 3 all raised to the second power. Well, we could do this with what we know, because we could multiply the 2x plus 3 times 2x plus 3, and of course we get 4x squared plus 6x plus 6x is plus 12x plus 9. And so this would be the antiderivative of 4x squared plus 12x plus 9. And we integrate with respect to x. And then if we go through here, all right, notice the antiderivative of x squared is x to the 2 plus 1 over 2 plus 1. So that would be 4 over 3, 2 plus 1, x to the third, plus 12, this is x to the first, x to the 1 plus 1 is 2 over 2, so this 12 divided by 2 is 6, so this will be 6x squared. Then plus the function whose derivative is 9 is 9x, and then plus c. So there we found it. There's the antiderivative of that quantity 2x plus 3 squared. All right, however, if we look at this problem, 2x plus 3, the antiderivative of 2x plus 3 raised to the 12th power, all right, that gets a little bit tougher because it's going to be hard to raise that to the 12th power. So what we would like a technique that would allow us to take the derivative, or the antiderivative, of 2x plus 3 raised to the 12th power as easily as we take the antiderivative of 2x plus 3 raised to the second power, and in fact perhaps easier than what we've done just now in this example. So what we have to do is we have to recall the idea of the chain rule. All right, notice if we have a composite function, one function, capital F, evaluated at another function, g of x, all right, then the derivative of that composite function, the derivative of capital F of g of x, is the derivative of the outside function, derivative of capital F, evaluated at g of x, times the derivative of g of x. Well, if that's true, when we take the derivative of f of g of x, capital F of g of x, we get capital F prime of g of x times g prime of x. When we anti-differentiate, capital F prime of g of x times g prime of x, all right, excuse me, we get back to f, capital F of g of x. Notice, and this is how I like to think about it, notice this factor of g prime of x. All right, this g prime of x is manufactured in differentiation. All right, and it is annihilated or destroyed, I'll say, because I don't think I can spell annihilated. It's destroyed in integration. Now, if you knew all that, and it could be cagey about applying this, all right, you would never have to use u-Substitution. However, what u-Substitution does is u-Substitution just helps us take care of the bookkeeping of this to cut down on mistakes. So let's take a look at how u-Substitution works. All right. Well, before I do that, let's look at this in a couple more instances. I guess examples. If we wanted to take the derivative of x squared plus 5 all raised to the 7th, that would be 7 times x squared plus 5 raised to the 6th times the derivative of the inside function 2x. So the antiderivative of 7 times x squared plus 5 to the 6th times 2x is going to be x squared plus 5 to the 7th. Okay, notice under differentiation we created this derivative of the inside function 2x. Under integration we used it up. Okay. Another example, the derivative of the cosine of e to the x is the opposite of sine of e to the x times the derivative of e to the x, which is e to the x. So antiderivative of negative sine of e to the x times e to the x is going to be cosine of e to the x. Again, now as these get more complicated, we have seen where everything comes from, in here, because we just took the derivative and we were aware of where it came from. But sometimes as things get multiplied and mixed together and stuff like that, we might not be so aware of it. So again, the u-Substitution will help us to take care of that, will help us to take care of the bookkeeping. So let's recall where we started. The derivative of capital F of g of x with respect to x is capital F prime of g of x times g prime of x. So the antiderivative of capital F prime of g of x times g prime of x is capital F of g of x plus c. And let's let u be the inside function, in this case g of x. Let's u be the inside function. Then we could look at this in a couple ways. If I took the derivative with respect to u of f of u, I would get f prime of u. So if I take the antiderivative of f prime of u with respect to u, I get back to f of u. All right. If I take the derivative of f of u with respect to x, I get the derivative of f of u times the derivative of u with respect to x. So if I take the antiderivative of f prime of u du dx, but now with respect to x, because this derivative was with respect to x, I get back to f of u. So notice we have two ways of writing, all right, capital F of u plus a constant. Either it's the antiderivative of f prime of u du, or it's the antiderivative of f prime of u du dx. So we have these two things are the same. These two things are the same, that the antiderivative of f prime of u du dx is equal to the antiderivative of f prime of u du. Now compare this with the results of when we talked about differentials in section 3.5. We had defined, all right, if u was a function of x, then du was the derivative of u with respect to x times dx, which is just what this is saying, that this du is the derivative of u with respect to x times dx. So we actually are, that's actually a sort of another, how could I say that, verification or of that notation. It's just that it's helpful. All right, now let's take a look at this. All right, let's go back to this problem that was going to be hard to take the antiderivative of. All right, let's take a look at the antiderivative of 2x plus 3 to the 12th dx. Well, in what we've said, remember we let u be equal to g of x, and g of x was the inside function. So notice the composite function here. We have 2x plus 3 is one function, and then that function is being raised to the 12th power. That's our composite function. Let's let u be the inside function. The inside function here would be the 2x plus 3 all right? And if u is 2x plus 3, du dx is going to be equal to 2. Du dx is going to be equal to 2. Well, now if I could create that du dx in here, I could call it, I could replace this with du. So I could rewrite this way. This is the integral of u to the 12th dx. So wrong variable. All right, but let's see, what I could do with this is, let's do the following. Let's integrate u to the 12th, all right, times 2 times 1/2 dx. Okay, let's integrate this. Okay, notice I haven't changed anything. I just multiplied by 1. This 1/2 is a constant factor, so we can take it out of the integral. And now we'll have the integral of u to the 12th, all right, times 2 times dx. And notice, excuse me, notice this 2 is the du dx, so this would be 1/2 antiderivative of u to the 12th du dx dx. And this, remember, this expression was du, so this would be 1/2 antiderivative of u to the 12th du. And that, of course, now it's easy. This is u to the 12 plus 1. U to the 12 plus 1 over 12 plus 1 plus a constant. And now we just have to remember what u was. U was this 2x plus 3, so this would be 1 over 26 times 2x plus 3 to the 13th plus a constant of integration. And there we have it. Now, I've gone through a lot of steps here, but once we get used to it, we won't have to go through quite this many steps. Let's take a look at another example, quick example, and go through this a little more quickly as we typically would, or at least as I think about it. All right. Okay, so let's take a look at this. We'd like to integrate 3x squared, all right, times the quantity x cubed plus 1 to the 12th. All right, so let's see, what's u going to be? It's going to be x cubed plus 1, the inside function here. You look for a composite function, and then the inside function of that composite function is u. Then du dx is equal to 3x squared. Now, there's something that I would say is, you see, we can multiply and divide this sort of like we can just perform algebra on it. Du dx times dx is equal to 3x squared times dx. This is du is equal to du dx dx. Remember our differentials from 3.5 is 3x squared dx. Then dx is going to be this du divided by 3x squared. So notice that I could make a substitution in here. I have 3x squared, then I have u was x cubed plus 1 to the 12th, times du over 3x squared. And notice the 3x squareds cancel, and I'm left with u to the 12th du, so that would be u to the 13th, 12 plus 1 over 13, plus a constant, and now just replace the u with this x cubed plus 1. And there we have it. That antiderivative would be x to the 3rd plus 1 all raised to the 13th divided by 13 plus c. We'll do some more examples in the next 2 videos.